In this question, Tina wants to determine the minimum possible cost of building a three-dimensional safe with the different cost considerations shown in the question. Well, it's kind of a lengthy answer because we are going to discuss the domain issues a little bit. So I'll try to give you a screenshot of the whole thing if you want to see an overview. Okay, and so now what we're going to do is go through the thinking step by step. We see that the volume is 1 meter cubed. 1 meter cubed is obviously a meter times a meter times a meter. Converting to centimeters, we see that that's the same as 1 million centimeters cubed. Now, the volume is length times width times height. We have a square-based rectangular prism, which means the length and the width equal each other. So we're going to let that value be x, and we can say that the volume is equal to x squared h. So in other words, 1 million equals x squared h. Well, we can divide both sides by x squared, and we can say that h is therefore equal to 1 million over x squared. Now, since the floor is $1.50 per square centimeter, and we have an area of x times x, we can say that the cost of the floor is 1.50 x squared. And the cost of the ceiling is 0.50 x squared by similar considerations. Now the wall is 80 cents per square centimeter, and the area is x times h, because each of those walls has a length of x and a height of h. And since there's 4 of them, we multiply by 4. Well, subbing in 1 million x to the negative 2 for h means that our cost, when we add these two terms together, is 2x squared plus 3.2 million x to the negative 1. Now, we have a cost formula. What we're going to do is try to figure out what the domain is of x with respect to this formula. Well, we know that the height has to be between 40 and 200 centimeters. So 40 is less than or equal to h is less than or equal to 200 centimeters, and we sub in 1 million x to the negative over x to the negative, or excuse me, 1 million over x squared for h. Now, we have this inequality, and we'd like to isolate the x. What we're going to do is take the reciprocal of all three sides. When we do that, what's going to happen is we're going to change the direction of the inequalities, because the bigger a number is, the smaller its reciprocal is. If you think about it, we would write 3 is less than 5, but if we took the reciprocal, we would say 1/3 is greater than 1/5. The same principle is at play here. So 1/40 is greater than or equal to x squared over a million, which is greater than or equal to 1 over 200. Now we're going to multiply all three of those sides by 1 million. And so what we're going to get is 1 million over 40 is greater than or equal to x squared, which is greater than or equal to 1 million over 200. 1 million over 200 is 5,000. 1 million over 40 is 25,000. Rearranging it so we can read from left to right, we see that this is one step away from our domain. Taking the square root of all three parts, we get 70.7 is less than or equal to x is less than or equal to 158.1. Remember that we're dealing here with positive numbers because it's side lengths that we're talking about. Now we're going to take the derivative of the cost function with respect to x and set it equal to 0. Doing that leads to the result that x is approximately equal to 92.8. So we're going to sub in our two n values for x, 70.7 and 158.1, and we get these relatively expensive costs of 55,000 and 70,000. And then we're going to let x be 92.8, and we're going to see that we get a minimum cost of $51,706.44.